This is lesson 7.5. Excuse me, this is the second NBA lesson. The first one was about the power forwards, so now we're coming back talking about shooting guards. And if you don't know basketball, shooting guards are not quite as tall as power forwards. So the main question today is similar to yesterday is how tall do you need to be to play in the NBA? And it depends on your position. So today we're doing shooting guards. And as yesterday, if you go to Schoology, you will see here here there's your lesson, and then underneath it is the on the bottom of the lessons folder there, you see the NBA heights for shooting guards. If you open that up, that pretty much answers question number 1. It says refer to this handout and describe the population distribution. So if you look down here, there are a couple dots. There's on the left side, and it has a tail on the left. So this set of data for all the shooting guards is skewed left. And that summary statistics right there tells you what the mean is and what the standard deviation is. So you can just kind of transfer those over into your notes. And we'll go from there. So this is really our target. So our average is 76.333 from the table, and the standard deviation is 1.673. So this is, if you wanted to label this is mu, and this is sigma, because those are the numbers for the entire population of all shooting guards in the NBA, and there are 123 of them. All right, so then we're going to do in class, we're going to do a sample of 2 shooting guards, and then we're going to repeat it for a sample of 10 shooting guards and find the averages of both and kind of see what happens. We're exaggerating. This is a ridiculously small sample size, and then we're increasing it to 10 and just kind of comparing. Okay, so they will both be sampling distributions when you're done. These 2 that you see down here, I grabbed those from previous classes and other years, but we're going to be creating these in class. So to take a random sample of 2, on your calculator, you can go to the math probability, do the random integer button. There are 123. I think I might have used this number yesterday on the power forward video on accident. I may have. But you want to do that, and you get a sample size of 2. So for example, for me, zooming in here, my heights would be what? The 33rd player had a height of 77 for me, and the 67th player had a height of 76. Add them up, divide by 2, and there you have it. So everyone in the class is going to do this for a sample of 2. So let me just see here. So for my sample mean, I would have 76.5. Oh, that's right, and that's coming back to me slowly, having a brain fart. We're going to do this, everybody in class is going to do this 3 times, okay? So I'll just walk through the motions. You can pause the video, do with this as you will if you need to. So the 47th shooting guard had a height of 74, and the 94th shooting guard had a height of 77, divided by 2, so they have a 75.5. Let me do it one more time when I'm here. Everyone's going to do this 3 times so that we have more samples to put on the board. 64, that person was 75 inches tall, and 83 was also 75. All right, well, that's going to be an average of 75. So I've got 75.5 and 75 for my last 2. Okay. 75.5 and 75. Okay. And then I'm going to have everyone come to the board. They're going to all put 3 dots on the board. So I should have actually a lot more dots than this. Okay. This is the sample when n is 2. Sorry, this is the sampling distribution when n is 2. Okay, this first one. And you can kind of see here, the shape is, it's pretty normal. I would say pretty normal, maybe slightly skewed left, but it's nothing crazy. Okay, and for the mean, where would this bad boy be centered, right? It kind of looks like it's right centered right about here, but what we learned yesterday is that the average x bar, just to be clear, these are all x bars, right? They are the result of a sample. They are statistics. If I take all of these samples and all of these dots and add them all up, it's pretty much would lead me here, right? It would lead me to mu, the population average, which I know to be 76.333. Okay. Um, and the standard deviation is not this. You might be thinking that. Remember what we learned yesterday. This is the standard deviation. You might even want to say this is for like choosing one player. Okay, we're not. We're choosing two players. So if you recall, you have to take your standard deviation, which is right up there, and you divide by the square root of n, which is the square root of 2. You can do that on your calculator, but you're going to get 1.18. Okay, so that's what we know is going to, the sampling distribution will look like when we are only taking 2 shooting guards at a time. Then the third question, we're repeating this, but we're just increasing sample size. So just to show you the process, and you could maybe do one. I realize you're not in class right now if you're watching this video, but it may help you to kind of just understand what we're doing, to go through the motions a couple times. So I'm going to do this for 10 shooting guards. Whoa, whoops. My bad. Let me start over. 1,123, a little German for you, and sample size of 10. So there you have it. Now, theoretically, I want to do this when I do not have any repeats, ideally. So I see 1, 2, 3, 4, 5, 6, 7, 8. I don't have any repeats there. 9, 10. I don't think I had any repeats. Oh, there's 285s. Let me just see if I can go again. Get no repeats. I don't see any repeats there. 85. Oh, came up again. You guys are gathering that these random tables maybe aren't as random as you thought, but it's the best we can do. There you go. I got 10 random numbers. So then we're going to match them up just to drive this point home. So person 118 is 78 inches. Person 73 is 74 inches. Person 81 is 77 inches. Yes, this is going to take a while. You're going to add them all up, and then you're going to divide by 10. Excuse me, okay? And everybody in class is doing this 3 times, okay? So it'll be time consuming. I have 3 samples from students from previous classes, 76.1, 76.6, these are just placeholders really, and then 75.9, okay? And then everyone is going to take their 3 samples. They're going to come to the board and put dots on the board, okay? Sorry for my scratchy throat. All right, and then here's an example of what a classes would look like, okay? We're probably going to have way more dots than this again, because if I got like 25 kids per class and every kid does 3 samples, this sampling distribution should have 25 times 3 dots. Because remember, every dot is the result of like one sample, so to speak. Okay. So what do you notice about this distribution? Well, right off the get-go, I notice that it is more tightly grouped than the one above it. the dots are not as spread out, and I notice that it is even more normal. Okay, so the shape, I'm gonna say now, it actually looks to me to be approximately normal. Approximately normal. Okay, now there's a note here to remind myself here. To be considered approximately normal, to be safe, we want the number of samples, sorry, the number in my number here to be at least 30, okay? And right now we only have 10, okay? So this has a title. This is called the central limit theorem. So when we're doing sample averages, sample means is the way we say it in the stats world. When we're doing sample means, to get to being approximately normal, we need the n to increase. And as it increases, you can see here the first one is slightly skewed left, and it's skewed left, and this one is now more normal because I've increased it to a sample size of 10. Okay. And this, if I continued, if I made you go back and do more shooting guards, like 20 or 30 shooting guards, yes, it would take forever. But what would happen is this curve would tighten up and it would become even more like the normal curve. Okay. Now we'll see what we can do here. Number 5. Use a normal distribution to find the probability of taking a random sample of 30 shooting guards. Okay. I chose 30. Oops, sorry. I chose 30 because to be safe. Oh, hold up. Let me back up. I realized I just skipped these two. Um, the average would be the same as the one above it. The average X bar would be 76.333. And it kind of looks like that. Like 76.3 would be right about here, right? That looks pretty close. And the standard deviation now of this one, it's not going to be the same, right? Up here, because this was a sample size of 2. So if I just duplicate this and bring this down here, it's going to be almost the same thing, but I'm dividing by the square root of 10, which I'm dividing by a larger number, so my standard deviation is going to be smaller. And this is, you saw all this right away. Look at this curve. This curve is not as spread out as the curve above it, okay? All right, now sorry, back to number 5. So now my sample's 30. What's the probability I do this? I add up all 30 shooting guards' heights, divide by 30, and I get a mean more than 77. So remember, this is my sampling distribution down here. It will be centered at mu, which is the height of the average height of all the shooting guards. It's centered there. And I'm asking, 77 is over here. What's the probability if I did this? I would get a sample average higher than 77. We know that this curve will be centered at 76.33. I guess the question mark is, what is the standard deviation? Well, the standard deviation of this X bar, of this sample, would be 1.673, and this time I'm dividing by the square root of 30, which is going to further tighten this curve up. So I get that. You can take your calculators out and check my work, 0.305. All right, so now I'm going to get a z-score. My value of the sample is an average of 77. The mean of all of the entire population is 76.333, and my standard deviation is 0.305, giving me a pretty big z-score of 2.19. We know there's not much data beyond 2 standard deviations, but at this point, you could put your 2.19 here, and remember it keeps going way out to 99. You could do your normal CDF, and 2.19 comma 99, boop, and you get about 1.4%. You could also use your green packets if you wanted. So the probability that X bar would be greater than 77 in this situation is about 0.014. Okay, 1.4%. All right, so what did we learn? One of the big takeaways is this, the central limit theorem, which I mentioned above, that these sampling distributions of the average of X bar is approximately normal when n gets large enough. When your sample that you're grabbing is at least 30 items that you're going to average. Right? So that's what we learned right up here. 2 wasn't enough because it was still slightly skewed left. 10 looked better, but it wasn't enough. The accepted cutoff in AP Stats is 30 to be safe. And essentially what's happening is this, right? As the sample size increases, the sampling distribution becomes closer and closer to matching the normal distribution. This is true even for populations that had skewed data to begin with. Because remember, the original distribution way up here of all of them was skewed left. And that won't matter, you guys, because um, let me see, let me go back to Schoology, because not that it doesn't matter, but so this is the original population right there. It's skewed left. When I take a sample, I'm not just like sampling the dots and then remarking them on the distribution. I'm taking the dots, I'm adding them up, and I'm averaging them. So over and over and over again, I'm going to be finding numbers that are close to this. Sometimes they're going to be too high, sometimes they're going to be too low. And what the central limit theorem says is that as n gets big enough, the skew that you see on the left, on my Schoology, on the document there, that skew will essentially think of it as being ironed out, or it will go away because as my sample size gets larger, my dots are going to be really close to the true average. Some are going to be too high, some are going to be too low, but that's the effect of the original skew in the data will be lessened. Okay, that's the idea. And then last little bit here. So the normal distribution is centered at mu, which is the average of all the samples, which is the population mean. And then don't forget that we did this once, we did it a couple times. The formula for this is sigma divided by the square root of n. The population standard deviation for one person divided by the square root of the sample size. And then that determines your curve, it determines how to get a z-score, and then you use table A. That's it, folks. Later.